Hello and welcome back. If you're new here, make sure to subscribe for more programming tutorials. Today, we're exploring the merge sort algorithm. Let's dive into how this powerful tool streamlines sorting processes in computing. Here's what we'll cover today. First, what is merge sort and why is it important? We'll introduce the basics of merge sort and discuss its significance in computer science. Second, how merge sort works with illustrations. We'll explain the process step by step, using clear illustrations to help you understand each part of the algorithm. Third, understanding time complexity. We'll analyze the time complexity of merge sort and why it's efficient for large datasets. Let's get started with a detailed look at what merge sort is and why it's a crucial part of sorting algorithms. Let's start by understanding what merge sort is and why it's such an important tool in the world of computing. Merge sort is a type of sorting algorithm, a method used to organize and order data. Imagine you have a deck of cards scattered all over a table. Sorting them means arranging these cards in order, say from ace to king. Merge sort helps perform this kind of organization, but it does so very efficiently with data in computers. Now, why is merge sort important? In computer science, sorting data is a fundamental task that helps make more complex operations possible and efficient. For example, finding a name in a sorted list is much faster than in a mixed-up one. Merge sort is particularly valuable because it's very efficient with large amounts of data. It splits the data into smaller pieces, sorts each piece, and then merges them back together in order. This divide-and-conquer approach allows it to work faster than some other sorting methods, especially as the amount of data grows. By using merge sort, computers can handle large databases, like those used by search engines or social media platforms, much more quickly and effectively. This capability is crucial for the tech that powers our daily lives, from searching the internet to streaming videos. Understanding how merge sort works gives us insights into the behind-the-scenes of these everyday technologies, showing us just how important these algorithms are in our digital world. Now, let's dive into how merge sort actually works. To make this easy to understand, we'll go through the process using a specific set of numbers. Here they are: 15, 14, 55, 7, 9, 49, 16, and 21. First, merge sort divides the whole list into smaller groups. It breaks down the problem into manageable parts. We start by splitting our list into two halves. On the left, we have 15, 14, 55, and 7. On the right, we have 9, 49, 16, and 21. Next, each of these halves is further divided. On the left, we split 15 and 14 apart from 55 and 7. Similarly, on the right, we separate 9 and 49 from 16 and 21. Now, we keep dividing until each subset has just one element. So, we end up with individual numbers: 15, 14, 55, 7, 9, 49, 16, and 21, each in its own group. The next step is where the magic happens: merging. But as we merge them back together, we sort them. We start with the smallest groups. We compare 15 and 14, since 14 is smaller, we place it before 15. We do the same with 55 and 7, placing 7 before 55. We repeat this for each pair. After sorting individual pairs, we merge these small sorted lists into bigger ones, all the while keeping them sorted. For instance, the sorted pairs 14 and 15 will be merged with 7 and 55, but in order 7, 14, 15, and then 55. Finally, we merge the sorted halves back together into a single sorted list. From our right half, sorting and merging have given us 9, 16, 21, and 49. Combining everything gives us our final sorted list: 7, 9, 14, 15, 16, 21, 49, and 55. And that's merge sort. By breaking down the list, sorting small parts, and then merging them back together, merge sort effectively organizes the numbers into a sorted order. Let's talk about how fast merge sort can sort data and why it's a preferred method, especially when you're dealing with big lists. First off, what is the time complexity of merge sort? It's O(n log n). But what does that actually mean? As we discussed, every time you use merge sort, you split the list in half until each piece has just one item. That's the log n part. It's about how many splits you have to make. Then, you merge these items back into order, and each merge involves checking each item at least once. That's the n part. So, the total effort involves going back and forth through these steps, which is pretty efficient when you have a lot of data. Now, let's compare this to other common sorting methods like bubble sort or insertion sort, which often have a time complexity of O(n squared). In these methods, you might end up comparing every item to every other item, which gets really slow as your list grows. For a small list, you might not notice much difference, but as your list gets bigger, O(n can become painfully slow compared to merge sort's O(n log n). This efficiency is crucial in real-world applications. I hope this gives you a clearer understanding of why it's such a powerful tool in computer science. Thanks for watching. If you found this helpful, please give it a thumbs up and subscribe. Any questions or requests? Comment below. See you next time.